Okay, so we are talking about union operation, how we can perform the how we can do the augmentation in the W connected linked list. We have seen we are going to we are going to add a pointer from each element to the representative element, that is the first element, because this is W connected linked list and our first element is the representative element. So, we are going to have. So, now we are talking about the union operation. So, the union of two set, union of S y. So, basically S x. So, basically you have two sets S x and y belongs to S y. Now, we want to have the union of these two sets. So, that we want to do. So, this is set S x and this is set S y, S is here, y is somewhere here in one of this. So, for the union what we are doing, we are just so we are doing the union. So, union is basically S x union S y. So, for that we are just adding this. So, this last pointer we are just adding this, and then this pointer also we have to change. So, this was the now this first element is the representative for this also, all these nodes. So, this we are going to change now. So, for these nodes also, all these nodes having the representative element S 1. So, this is the operation we are performing. So, this is the union operation. So, how long time it is taking? So, this is the bigger set. So, now the bigger set, if it is order of n, then we are just taking theta of n times, because everybody has to change the pointer, because this is the bigger set. Now, so what is the idea? Idea is to, so instead of merging this with this, if we merge that does not matter, if we merge this with this. So, that is the trick one. So, we merge the smaller set with into the bigger set. So, that is the idea of trick 1. So, then we can save some time, because this is if this size is n and if this size is some constant, then hardly we are changing the pointer of this side. So, that is the idea. So, instead of this what we do, so this is our S y. So, everybody was pointing here in S y. Now, this was pointing here. Now, we are merging this set with this set. So, this is the at the end. So, this is, let us write again. So, instead of merging S x with S y, we are just going to merge. So, this is our union now. So, this is x 1, sorry, this is now y 1. So, y 2, y 3, and now we are merging this. This is the smaller set x 1, x 2. Now, all this y have, this was S y, and now this was pointing here and it pointing itself. Now, we have a connection over here, and this all these are now pointing to here. Okay. So, this is the trick. The trick is we want to merge the smaller set with the larger set. So, that way if this size of this is constant, but in the worst case it is order of n, but we will do the amortized analysis on this and we will see this operation will take log n time. So, this is the idea. So, this is the idea of merging the smaller set with the bigger set. So, now the question is how to get the smaller set. So, the idea is to this is the trick 1. So, trick 1 we apply on. So, trick 1. So, that is smaller set, smaller into larger. So, this idea, this type of trick we will use in a lot of other places also. Okay, so, the idea is to concatenate. So, we are concatenating two lists. So, concatenate smaller list onto larger list onto the end of the larger list. Okay, so that is the idea. So, we are just because the earlier we are doing S is why we are concatenate with S, but S is smaller. So, now we after applying the treat we are going to use the S is smaller. So, we are going to concatenate S in at the end of Y list. So, that is the idea. Now, the question is how we can decide which list is smaller and which list is larger. Then we need to try get the length of the list. So, again if we have to calculate the length, then we have to traverse the list. So, that will take again linear time. So, to save that we have to do again the augmentation. We augment the list to store the size of the list, to store, that is called weight, to store its weights. Weights means number of elements. This is the number of elements. So, this is the new augmentation we have to do. So, we are going to store the on each element we are going to or in the beginning, because we are anyway we have access to the representative element. So, there we can store the size of the list. So, so suppose we have given this is a list, and every pointer pointing here say. So, we have given a x. Now, we can reach here somehow if we can store the weight of the list. So, this is S I or this is x I. So, then we came to know which one is larger and which one is smaller. Then we can apply this trick. Okay. So, if we apply this trick, then what is the time for doing this union? Because so we are just not bothering about the find operation, because find operation augmentation we did and we can solve it constant time. So, we are only concerned here is now the union operation. So, how much time it will take for union? So, union cost is basically theta of length of the smaller list or weight of the smaller list, length of smaller list. Okay. So, now we have to go for amortize analysis to show the average cost is log n. So, for that we have to do the amortize analysis. So, let us this is the without amortize analysis, this is the. So, now we have to do the amortize analysis. So, for that let us just denote some. So, let n be the overall number of element, overall number of elements. So, total number of elements. So, these are coming by say make sets. So, every time we are making set and doing the union, and we are. So, overall, so this is the total number of order of n times we are doing the make set. Okay. So, this is basically equivalently number of make set operation. So, that is how we get the elements na. Once we make set, we get a singleton set, then we union. So, this is the way we got the elements. So, this is the number of make set operation. This is the way how we get the set. So, M is the total number of operation. Total number of operations, and F is denoted by the number of find operation. So, number of find set operation. So, these are the notation we will use in our time complexity, in our amortized analysis. Okay, so now we are going to prove a theorem in a amortized sense, that the cost of all unions, because we are worried about union for these argumentations, is order of n log n. There are n elements overall. So, if cost is order of n log n in a amortized sense, then the average cost is, there are n element, average cost is log n. So, that way we are going to prove this. So, let us prove this theorem. The cost of, total cost of union operation is n log n. So, okay, so let us just state this theorem. So, the total cost of unions operation is order of n log n. So, how to prove this? So, this is in amortized sense. Okay, so, we basically we choose a x and we monitor x. We monitor an element x. We look at an element x, we monitor x and its sets, and set S x containing x. Okay. So, we will see how many times it is getting changed and what is the happening with this. So, that is of our interest, and there are n element. So, we can just multiply with that. Okay. So, we want to see the cost for this union, overall cost for this union for this particular element x, okay. And there are n elements. So, we will multiply that. So, if we can show that for this x we are just doing the how many times, we are just doing the log n times, then overall we are doing n log n times. So, that is our goal. Okay. So, how to prove? So, that is basically, so after initial, so how we are getting x? So, after initial make set. So, we got x by doing the make set operation. So, that time weight of x is basically 1, because that is the singleton element, and we in the union operation we unite x, we merge x with some other y. So, each time S x, the set which containing x is united. So, while we are doing the union operation with S y, united with a set S y. So, we are just, when we are doing union of x and y, so we are doing this. So, now our trick is we are going to merge the smaller set to larger set. Now, if this weight of, so if the S is Sx is smaller set, then only we are going to change all the element of Sx to this. So, that is the idea. So, that means if the weight of Sy is greater than weight of Sx, then Sx is smaller, then Sx is going to march with Sy, and then we are changing all the pointers of Sx to the representative pointer of Sx, all the elements for that, and then we are paying some, we pay 1 to update. So, if this, if okay, Sx comma, then we pay 1, say $1 to update rep of Sx, because then we are going to, because this is the smaller set, then rep of Sx. So, that means and then the weight of Sx, then Sx and Sy will be replaced by the union, then the weight of Sx. So, then the weight of Sx will be how much? The double, then the weight of Sx will increase by at least double, because the weight of Sx, weight of Sy is greater than that. So, weight of the new set will be the weight of this plus weight of this. Now, so it will be double. So, that is why this 2 is coming, that log n is coming. So, that is the reason this log n is coming. So, this is basically increasing the because the weight is increasing by the weight of Sy, which is basically greater than Sx. So, that means weight is becoming double. So, that is the reason this log n is coming, log n base 2. Okay. And if Sx is more, if Sy is united with Sx, then we are not paying anything. So, then the how many times we are doubling? Then we are doubling just log n time. So, we are just making double is less than log n base 2 times. So, this is the proof. So, that means that is why the log n is coming, because it is doubling. So, this is the proof. So, the total number of operation is, so this is the proof. Okay. So, this is the one first trick. Now, in order to bring the second trick, so this analysis is amortized sense. So, amortized sense, our total time complexity is, the total union operation is n log n. Okay. Now, if we have, so we have taken the one x, for that x it is log n. So, there are n elements, so it is n log n. So, this is the total cost in a amortized sense. So, now average cost is log n, but for few cases it is more, like in, but amortized sense it is average cost is log n. Okay. So, now we will discuss the second trick, trick 2. For that we need to bring the data structure, which is tree. So, let us again bring the tree representation, representing sets as tree. So, here we are not dealing with binary tree, or it is not a balanced tree. So, suppose we have a set x, x1, x2, xk. Now, we store this into a tree, and this tree is unordered. because our sets are unordered collections, unordered, unbalanced. Here we are not bothering about balance. Okay. So, and not necessarily binary, not a binary. I mean, it could be any tree. I mean, the children could, number of children could be more than 2. It could be 3, 4, it could be 2 also, it could be null. So, it is not necessarily binary tree. Okay, it could be ternary, it could be, I mean, it is not necessarily binary tree, and the parent is basically the root. Root of the tree is the representative element. Rep of Si. So, basically we have a tree. Okay, so let us take an example. So, suppose we have a set, say x1, x2 dot 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 x6. Okay, so let us draw a tree x1, x4, x3, x2, x5, x6. Okay, so this is not a binary tree, and this is not a balanced tree also. So, we do not care about that. So, now we only have, we do not have child pointer, we only have parent pointer, and this is the root. Rep of Si is this one, the root of the tree. So, we only have the parent pointer of each node. So, we do not care about the child, because no need to care about the child pointer. So, this is the root. So, you only have the parent pointers. Okay. So, why we need parent pointer? Because to find the set. So, we have to return this root element. So, if we have parent pointer, so suppose we want to, this is our xa. Suppose we want to do the find set of x5. So, what we do? We look at the parent pointer this way, we reach to the root and we return x1. Okay, so, that will take height of the depth of x basically. Now, this is our data structure. Now, how to perform this operation like make set? Make set is easy, just we make a this tree, I mean a singleton tree, that is it. And the find set is this one, and union. So, find set will take how much time? Find set will take order of depth of x. This is the find set cost. Find set will take order of depth of x. Now, what about the union? Union, suppose we have another set y, y1, say y. So, we have another set sy, y1, y2, y5 say. So, y1, y4, y, this is another tree we have y2, y5. So, now this tree is also like this, we have only parent pointers. Now, how to find set? So, we can add this root to any one of this node, that will do, because if we add this root to any one of this node, then the we can just from this we go to that node and then we visit to the root, or else we can just add this to here. So, this way we can do. So, this is the union operation we are doing. This is the union operation we are doing. Okay. So, now the question is, if we adopt the trick one here. So, if we adopt the trick one here, so that means if we just add the smaller set to the larger set, then how it is helping us. So, that is the next discussion we are going to do. So, this is called this set is completely unordered. So, this is the trick 1 adapted to trees. So, we adapted trick 1 for. So, that means, if we just find the smaller is merging with larger. So, if we can find the smaller tree, then we can add it to the larger set. Then the find will take the same time as find of x, okay. And height of the tree will increase, because height of the tree will not increase, because we are having smaller set, we are adding merging with the larger set. So, height will remain same. So, this is the trick 1. Now, let us talk about trick 2. So, that is the trick 2, which is also referred as path compression. Okay. So, what it is telling? Now, this is telling all about the find. Now, so when we perform a find operation, say we are performing the find operation on this set, say x 5 or say x 5. So, or say we are performing the find set operation on say y 2. So, if we perform the find set operation on y 2, what we go do? We go to the parent of this, then we go to this, then we go to this. Okay. Now, if we do this, now, so once we got the parent of this, we have a parent pointer from here to here. This is the new augmentation we are doing. So, that if the next time we again search for the find y 2, then we will get it directly. So, this is a path. Not only this, so we are going to add the parent pointer for each of this node in this path. So, that is the idea of trick 2. So, that is called compression, path compression. So, let us write that. So, when we execute a find set of a node, find set operation, and walk up a path P to the root. So, we know the representative. So, we got root, we are going to change the representative element of each node in that path. So, if a node y j belongs to this path P, then we are going to change the rep of y j to be x 1. So, we are going to have a direct pointer to this. So, direct pointer to this, all the elements in that path. So, this is called trick 2. So, this is the operation we are doing. So, this is basically called compression, path compression. So, instead of only one element, we are just compressing the path. I mean, we are taking all the node, representative element of all the node, we are changing to this root. Okay. So, this we can have a theorem to show this is in amortized sense. The total cost is, so let us just write the theorem, we do not have time to prove it. So, just we will state the theorem. So, this theorem is telling the total cost of find set is order of m log n, amortized sense. So, this is the amortized analysis. So, there are m times we are doing these operations. So, now the on an average it is log n. So, this proof we are not doing now, we do not have time. So, now this is if we only apply trick 2. Now, if we combine apply trick 1 and trick 2. So, that is the combination of trick 1 and 2. So, this is more interesting. If we apply both the tricks, then this is the general case, this is another theorem. In general, if we apply both the trick, the total cost is order of m log n. So, this proof is there in the Corman book. I am not going to do this proof. So, this is again in amortized sense. Okay. So, this is the amortized analysis we did for our data structure augmentation, and we apply the two trick. One is the we are going to merge the smaller with the larger, we are going to combine the smaller with the larger, and the second one is path compression. So, we are going to change each pointer of this representative element of each pointer of this set node on this path to the root. Thank you.